This is Rahul Joshi. I'm going to talk about how Rust is powering modern data lakes. I'll start with my introduction quickly. I work in data architecture, data platform space. I've been in the industry for around 20 years. Been working with large scale financial services companies to build modern data platforms, near real time, analytical, and data based applications. Yeah, with that, let's start the conversation. So first we are going to look at the landscape of enterprise data architecture, which has actually undergone a fundamental transformation over the last 15 years or so. I have laid out three different phases here. Phase one, which is on-premise Hadoop era, around early 2000, where Hadoop was launched. It had two primary components, HDFS and MapReduce, which dominated big data processing, large-scale data processing with JVM-based technologies primarily to handle massive data sets. It was a big hit, but it had some limitations. And to meet the performance needs, some of the limitations were related to garbage collection overheads and memory management issues. Lately, after a few years, in mid 2010s, cloud data warehouses were launched, which were primarily targeted to overcome the limitations of Hadoop and to meet the performance criteria and solve more usability problems, support analytical applications and SQL-friendly applications. So Snowflake and Redshift are some of the examples there. And then more recently, Lakehouse is trying to converge the data lakes and cloud data warehouse to give you the best of both. And that is achieved using open formats, unified processing, and separation of storage and compute. And also, Rust has emerged as a critical technology for modern lakehouses. So, we are going to deep dive into these three phases in the rest of the conversation here. So, why Rust for data infrastructure? Rust has a unique value proposition. Uh, Memory safety without garbage collection. No garbage collection policies are required during critical large-scale data processing, especially those jobs which runs for a long time. Type system its data bases at compile time, and it also allows parallelism for multi-core effective utilization of multi-core compute infrastructure. And it gives you predictable resource usage with deterministic memory management. So let's see how phase one limitations were, what phase one limitations were. So first is JVM based tasks. Right? Hadoop was primarily used to have tasks, map tasks, and reduce tasks. And in Hadoop was basically JVM based execution. So each task used to need its own heap space. And the object representations added 12 to 16 bytes per instance. And as you scale, it used to create many maps and many reduced tasks. They used to exchange data which needed to deserialize the data, right, before and after the exchange, which added the deserialization cost to know the data movement between JVMs, which was very significant in terms of CPU and memory need. And the third is the garbage collection pauses. Because it's a JVM based, it used to do unpredictable GC pauses, sometimes few seconds, causing a lot of inconsistent processing times and resource utilization. How Rust has created an alternative to MapReduce frameworks. So Rust has created alternative in a way, as you can see here, this chart shows the performance comparison of the word count, which is one of the popular benchmark in the big data, large scale data processing world. And as you can see, Rust is actually finished. The latest data fusion, which is based on Rust, has finished the word count on the large scale data in 8 seconds. So it has broken all the records and it's super fast compared to Hadoop, Spark, or even Rust Rayon. So Rust based implementations of all the frameworks basically eliminate GC pauses while providing more predictive resource utilization. And we are going to see more on this in the further slides. So phase two was the cloud data warehouse. We talked about it. Some of the examples of these are Snowflake and Redshift of the world. And the primary limitation there is in order to use these cloud data warehouses, historically, you needed to load data there. So they used to store data in proprietary formats, like Snowflake stores data in the packs, which is their hybrid columnar storage format, like PixSQL and Redshift store data into their proprietary formats. which created a vendor lock-in for the enterprises. So if you want to load data into these platforms, it's going to create a lock-in for you because it's going to have an egress cost to take data out later. And you're going to use compute to load data and compute to query the data. So that was a big limitation there. And the model of the compute was the model for the compute price was paper compute, which was incentivized for optimization, but it limited the control over execution. If you want to scale just storage or compute or vice versa, storage and compute used to be tightly coupled. And additionally, there was very limited ML support. Primarily, these applications, these platforms were built for OLAP use cases, not machine learning use cases. So if you want to use data for ML use cases, you got to take data out and then use it in some other platforms, which has created some silos and duplicate data storage. So with that, let's look at all frameworks have recently emerged and components which have recently emerged, which are powered by Rust. So Apache, you might have been familiar with, which is a columnar memory standard. It's a Rust-based implementation providing zero copy access to columnar data with predictable memory layout. It enables efficient processing across different languages and no serialization cost. Right? Data Fusion is another project which is powered by Rust to enable performance SQL capabilities. It's Arrow native and it provides both SQL and data frame APIs with physical query optimization. And the third one is efficient storage, Lance and Parquet RS. These are also Rust native implementations of columnar storage formats, delivering performance improvement of 3 to 10x, right, based on some of the recent benchmarks here. And in general, as you can see here, memory usage comparison for Rust-based query engines is typically 30 to 70% less based on some of the recent tests than JVM counterparts when while processing the same dataset. So that's pretty significant and powerful and game-changing in terms of infrastructure and efficient infrastructure and data processing applications. So let's look at phase three, right, which is where we are today, the modern lakehouse architecture. The lakehouse paradigm, as I said, it gives you the best of both warehouse and data lakes, and which addresses the limitations of both Hadoop era and the cloud data warehouse era. And it does that by using open storage formats. Some of those are Delta Lake, Iceberg, or Hoodie, which provides stable formats, which is ACID compliant. You can do ACID transactions, you can change schema. A schema can evolve over time, and you can also do time travel on the scalable object storage. It basically decouples compute and storage. It gives you ability to do single processing layer to serve both SQL users and machine learning users, which eliminates the need for redundant copy of data. The architecture is born scalable because you're decoupling your storage and compute layer. So separating them allows independent scaling of resources with governance and metadata management. So what is the role, Rust's role in Lakehouse architecture or Lakehouse infrastructure? So the key components that are powered by Rust today are table formats. There are table formats which allows you to interact with the Delta Lake tables or Iceberg tables using Delta RS and Iceberg RS libraries. It supports without going through Spark. So you can interact with these table formats without going through Spark compute, which is JVM-based compute, and native ACID transactions support with minimal overhead. Right? There are columnar storage format implementations which are Rust based, which we saw earlier, Arrow, Parquet, RS, and Lance, which allows predictive memory usage and zero copy data access. In terms of query processing, there is Data Fusion, which has emerged as a very promising project recently, and it allows parallel execution with minimal resource footprint. And last is data frame libraries. Polars and Arrow Data Fusion is 10 to 100x faster based on some of the recent benchmarks than Python pandas with less memory. So these are some of the powerful results that Rust has shown in benchmarking, which is going to radically change how the modern lakehouse architecture and infrastructures are built. And as you can see, some of the performance benchmarks was for Rust versus traditional technologies is 10x more query performance using data fusion compared to Apache Spark on the same dataset configuration and hardware configuration. 85% memory reduction required for Polar's data frame compared to Pandas while processing 100 GB datasets. 30x data, faster data loading. If you're loading data in an application from Parquet, you can load 30x more data as by using Arrow RS compared to PyArrow for terabyte scale datasets. So truly for large scale and enterprise scale analytical processing here. And 99.9% reliability, because you are not going to get out of memory errors, and there is no garbage collection needed for long running data processing jobs, which is one of the limitations for JVM based executions. So with that, I'm going to move to next slide. What are some of the practical implementation patterns? When I should use, how should I, if I'm using it, how should I optimize Rust? If I'm not using Rust, where should I use it? So there are three integration approaches, right? One is microservices components. You can identify critical data processing applications in your overall architecture and do Rust-based implementation and services and build the interfaces around it. So you can have highly performant and efficient applications as services, which could be integrated with other components in your architecture. Secondly, the extension libraries. You can create native extensions for Python on JVM as a core processing. And if you want, you can even replace your entire system or architecture for data pipelines and data processing with Rust alternative for the maximum benefit. Some of the common use cases where Rust really shines is high throughput data ingestion pipelines, which is processing millions of records or events per second. Large-scale data processing, feature engineering for ML training, right, to train your models and to identify the feature, which needs a lot of data processing, of course. Interactive SQL query engines requiring sub-second response time is another use case where we Rust-based application would really shine. So most organizations begin with targeted replacement of bottleneck components, which are already identified as a bottleneck, and then they start rewriting or replacing those components or services with Rust-based applications, and then doing a complete rewrite. And then at some point you might want to replace the entire application. Depends on what you're doing in your data processing and how much bottlenecks you have. So with that, we're going to talk about some of the key takeaways and the next steps. Rust addresses critical performance limitations. Just to recap, we saw it does not need garbage collection, predictable performance, and efficient resource utilization makes Rust ideal for data infrastructure. The Rust ecosystem is maturing rapidly with Arrow, Data Fusion, Delta Lake, and Colors libraries and Rust-based implementation. There are the whole landscape is production ready and evolving rapidly for high-performing data platforms. For organizations, I recommend you begin with isolated components analysis and see which interfaces can be replaced or enhanced or optimized using Rust. Focus on the bottlenecks first and then scale to the other components as well. So you can really use Rust's performance characteristics for building modern lake data platforms and future your architecture. So with that, I would say I recommend you evaluate your current data platform architecture and identify components that would benefit most from Rust's performance and reliability advantages. And that's it from me. I hope this was helpful and this information is helpful for you in your data platform modernization initiatives. Thank you for giving me opportunity and thank you for listening to my presentation.